Welcome back. In this video, I will go over how do we use the inverted drop weight method to measure the interfacial tension between liquid and liquid interface, as well as determining the adsorption isotherm. The drop weight method is one of the most convenient and accurate way for measuring surface tension in the laboratory. It is done by flowing the solution of interest through a nozzle, and we let the solution come out dropwise. Measure the weight of each drop to get the surface tension. This theory is quite simple that is proposed by Tate in 160 years ago, in which proposed that the gravitational acceleration or the weight of each drop is balanced out by the interfacial tension force, the surface tension force at the top of the drop. And the surface tension force is the surface tension multiplied by the perimeter. And the perimeter, if we have a circular nozzle, is 2 pi r. Therefore, we have W equals to 2 pi r of multiplied by the surface tension, sigma. However, such theory is an oversimplification because there are satellite drops that breaks away from the main drop, and there are also drops that leaves behind that attach to the nozzle. Therefore, we want to introduce a correction factor, small f, and we can also write it in terms of big F, where the big F is defined as 1/2 pi of small f, and we're written as W equals to the R, which is the radius of the nozzle, multiplied by the surface tension sigma, divided by the correction factor. The correction factor small f has the physical significance of the ratio between the weight of the liquid that breaks away to the total weight of dependent drop. At the instance of the breakaway. People have derived correlations for the correction factor, which we can use the correlation of big F in order to substitute and find out what the W or sigma is. And we note that the constraint is that F is a function of R and V is the volume of each drop. And the ratio between R and V to the 1/3 must be in between 0.3 and 1. After having the equation, we can then calculate the surface tension sigma, which is the weight divided and multiplied by F divided by R. And the weight we can see is just W equals to mg. However, we also have a buoyancy force that is posed by air. So the buoyancy force is a rho of air multiplied by g multiplied by the volume displaced, which is just the drop volume, the drop. So let's say we have air is phase 1 and the solution is phase 2. We have rho 1. And then mg can also be written as the density of the solution, rho 2 multiplied by volume times g. And therefore, the net force would be the absolute value of the difference between the density multiplied by g and v. That's the weight. Then we want to multiply by the correction factor divided by R. And therefore, we have an equation for the surface tension calculated by the drop weight method. Note that in the case of the air, we have a large difference between the density between air and the solution. So if rho 1 is negligible, then we can define rho 2 as rho. We will have rho v times g times F divided by R, and note that rho v is just the mass of the drop multiplied by g multiplied by F R. And note that the F is a function of R and V. Such simplification can only be done if the density between these two has a large difference. However, if we want to measure interfacial tension between liquid and liquid, we cannot use such simplification. We want to use the general form in which we take the difference between the densities. For example, if we want to calculate the interfacial tension between liquids, and in this case we have a liquid of water and the liquid of oil. And because oil has a lesser density, the oil will flow up. And that's why we have an inverted drop weight method where the oil rises in the water. And we want to measure the interfacial tension between the water and oil. And to do that, we want to use the interfacial tension formula that we derived before, where sigma is equal to the volume of the drop V multiplied by the difference, absolute difference between the densities, multiplied by g, gravitational acceleration, and f, the correction factor, that is a function of r and v, the radius of the nozzle and the volume of the drop, divided by r, the radius of the nozzle. And f can be used, calculated from the correlation here. The experimental setup is that we have a syringe pump that is filled with the target solution, in this case oil, and then the syringe pump pumps the oil into the device that goes through a nozzle, and after the nozzle the oil will be broken up and flow up to the water. And for the vent to be closed, have a closed system, and the displaced water will have to flow out side port. And we can measure the weight of the displaced water in order to find the weight of each drop. So that we measure, what we measure is the mass of the water being displaced. And then we can infer that it is equal to the mass of the oil drop. And from the mass, if we know the density of oil, which we want to measure through densitometer, then we can convert it to a calculated value of the volume of the oil drop. And from the volume as well as the radius of the nozzle is known, so R is known, we can calculate F. F is also a calculated value. After knowing R, F, G is also a known, gravitational acceleration. And we know the oil's density, we can also know the water's density, whether we make it a known by doing an assumption or we measure by densitometer. And the volume of the drop is known, and therefore we can calculate the interfacial tension. And the interfacial tension is between the water and the oil. Just to show you the experimental setup as well as the breakover of the drop, here's a video that I've done the experiment with, so that the drop breaks up quite interestingly, where we can see here we have almost vertical, and it breaks up, and we also see some satellite drops that forms. So that's why we need the correction factor. After knowing how do we calculate interfacial tension using the inverted drop weight method, we can then explore the effect of interfacial tension by the concentration of the solution. So in this case, Szyszkowski equation helps us to describe surface tension of binary aqueous solutions, where sigma is the surface tension and sigma 0 is the surface tension of pure solvent. R is the ideal gas constant. In SI unit is 8.314 joules per mole Kelvin. T, of course, is absolute temperature. Never use relative temperature. And B and A are the empirical constants. And they're usually called the Szyszkowski parameters. Natural log of 1 plus C2, and C2 is concentration. or molarity of the solute. Szyszkowski equation suggests that if we plot the surface tension with respect to the concentration of the solute, it will go like this. Where at the beginning, at the lower concentration range, there is a big decrease in surface tension or interfacial tension. But at the higher concentration range, the decrease is smaller. What we want to do in this experiment is to determine how lauric acid concentration changes the interfacial tension between the water and oil. That is because lauric acid has a hydrocarbon tail, and at the end it has a COOH group. COOH group. The hydrocarbon tail is hydrophobic, and the COOH group is hydrophilic. Because it is hydrophilic because it can interact with water by forming hydrogen bonds. So if we have a drop of oil, let's say this is the nozzle, comes off the nozzle and goes into water. Here is oil and lauric acid. And the lauric acid will preferentially orient itself so that the COOH group is at the outer surface and it can interact with the water. And in the inner surface, it is the hydrophobic portion that interacts with the oil. We want to determine how the concentration of the lauric acid will change the interfacial tension between the oil and water. And we want to find the interfacial tension for each concentration point so we can fit the line using the Szyszkowski equation and determine the empirical constants A and B. Usually we plot it at a normal coordinate. However, in this experiment, we will use quite a range of concentrations that spans around 2 orders of magnitude. So we want to plot it in a semi-log coordinates, where in the x-axis we have a log base 10 coordinate of concentration. For example, we have 10 to the minus 2, 10 to the minus 1, 10 to the 0, 10 to the 1, etc. And in that case, the Szyszkowski equation, the same equation, will look something like this. And you will determine that using your own data. Another thing we can do with lauric acid, as we have shown before, if we have a drop, goes. The lauric acid will preferentially orient itself so that COOH is at the outside interacting with water, and the inside is the hydrophobic chain that interacts with the oil. And we can use the Gibbs absorption equation at the ideal dilute limit to describe how much lauric acid is at the surface, so that the gamma 2,1 is the relative absorption of 2, which is the lauric acid of solute, with respect to 1, which is the solvent. It is equal to the negative of the concentration of the solute divided by RT, which is ideal gas constant multiplied by absolute temperature, and multiplied by d sigma divided by dC2, which is how interfacial tension changes with respect to concentration of the solute. You can determine this whole term using 2 methods. One, you can use the finite difference method, where we can just use the changing surface tension divided by the change in concentration. And because previously you will have determined at different concentrations what the interfacial tension is. For example, if we have a list of tables, it's just example data, and we want to determine the sigma C2 at some particular point, then you can use the points that are above and below to calculate. For example, for this case, we'll have 3 minus 1 divided by 3 minus 1 is just. However, this method is all from the data that you collected, so because it is from real data, it will be noisy. So the second method we can do it is to use the Szyszkowski equation that you have already fitted. So we have already know the B and A, then we can just take the derivative of sigma with respect to C2 of the whole thing. We know that sigma 0 is the interfacial tension of water, which is a constant, so it goes to 0. Negative RTB is constant, we can take them out. The derivative of natural log, we need to use the chain rule here. Derivative of natural log is 1 over x, so we have everything inside is 1 plus C2 divided by A is at the bottom, and at the top we'll have the derivative of everything inside, and the derivative with respect to C2 is 1 over A. We have calculated d sigma over d C2, and we substitute that into the original Gibbs absorption equation, which is negative C2 divided by RT multiplied by the derivative. Substitute that in, we have negative RTB multiplied by 1 over A and 1 plus C2 divided by A. We cancel out the RT and we rearrange this whole thing. Let's see, the negative also cancels out. We have C2B divided by A, 1 plus C2 divided by A. Let us further simplify this by multiplying A inside, so we have C2 times B, A plus C2. And that is our final equation. And because this is a fitted equation, we already know A and B, then we can have a continuous range of C2 that plugs in, and we can get that with respect to the relative absorption. So in this lab, I'm looking for a graph of relative absorption at the y-axis, and then on the x-axis I want the concentration. And this is called the adsorption isotherm because we perform the experiment in isothermal conditions. So delta T equals to 0. And on this graph, you will have the data points that you determine from finite difference method, where you have data points like this. And you'll also have the data you determined from Szyszkowski equation, and it will be a continuous range of C2 because you can vary C2 whatever you want. It would be like this. However, because in the data points you take, again, spans a range of magnitude, you might want to plot it in terms of a log base 10 coordinates. So again, you have 10 to the negative 2, 10 to the negative 1, etc. And that will give you something like this. In this video, I go over how do we determine the interfacial tension using the inverted drop weight method. And we want to explore the concentration effect on the interfacial tension. We can also determine the adsorption isotherm using the Gibbs adsorption equation.